Hi. Well, thank you, Frode, for inviting me. This is, I don't explicitly study text or its future. I have studied the history of an evolution of a part of the brain called the cortex for the past about 15 years. I'm going to try to tell you what I know about that history in about 7 minutes.
Wow.
And how it provides, I think, a really useful framework for understanding where text came from, and then what it could become, maybe even a little bit what it should become. This can be a much longer talk. I haven't given a PowerPoint presentation in about a year and a half now, and I'm very proud of that. But I'm also not very good at drawing, so we'll do our best. I'm going to draw only 3 pictures in the next 7 minutes, and they're going to be 3 different brains. This is the brain 500 million years ago, an early vertebrate. This is 3 major pieces, a forebrain, midbrain, and hindbrain. This is the spinal cord. We roughly know what the midbrain and hindbrain are doing. Hindbrain's in control of your movements, connects to the spinal cord. The midbrain integrates sensory information, makes sure that you do the right thing when you see a piece of prey or a potential mate. Do the right behavior. This forebrain bit in a fish, or 480 million years ago in all vertebrates, is still a bit more mysterious, and generally would be left out of a lot of the discussions about how brains create behavior if we didn't look at what happens next, which is where the forebrain sort of folds over to cover the midbrain and hindbrain. It expanded dramatically until about, say, 60 million years ago, between 5 and 60 million years ago, when you get to the earliest small mammals. This big explosion of the forebrain will lead to the first thing that I'd like you to remember from this talk, which is, if you remove that whole piece, which contains mostly cortex, but also something called basal ganglia, you can't tell what is behaviorally different about the animal that has cortex versus the one that has been surgically removed by a student in my lab. It is literally a dirty secret in neuroscience that rodents and a lot of small mammals missing cortex don't show any obvious behavioral deficits, which begs a huge question of why they devoted so much time over evolution as well as resources to main this thing. What is it good for? So I'm going to try to tell you what I think it's good for, and then a little bit what happens next. Very briefly, sitting with what would otherwise be a mouse or a rat. If you remove their cortex and you watch them, they do all of the behaviors that you're familiar with mice and rats doing, especially the ones we would test in the lab. Run a maze, learn to press a lever. They will mate and have kids and raise their children just fine. What we discovered about 5 years ago is that there's one aspect of the environment they do extremely poorly, which is when they encounter something unexpected. So when we had them walk across like an obstacle course, where one of the steps we can make unstable. So you step on it, it's like you're going up the stairs, and the 5th step you step, and it goes out from underneath you. If you were doing this in an environment that you understood, that you've been around, you know what's there, you might realize that you're in a stairwell, so you can grab the handrail. Or if if it's a slippery, icy day like almost this morning was, you might know that, oh, if I'm starting to fall, I need to brace myself completely differently. Or maybe there's a wall behind me. There's things about your environment that allow you to deal with that perturbation, that unexpected thing, much more robustly. Our robots right now are really good at a lot of things, but one thing they're definitely not is robust. And it turns out the only thing cortex seems to have been good for in a rat is to make them more robust when they encounter unexpected things. And so when they slip somewhere, if you lack a cortex, they do things that make no sense. And they actually look then, mostly, they look really clumsy, which is what you start to pick up on after watching them for quite a while. We talked just earlier after the last talk that I believe training robustness is really this process of play, of putting yourself in situations where you might encounter perturbations and learning how to then deal with them. How you deal with perturbations, dealing with things you've never seen before, requires having a model of the world. You need to have a more or less a simulation of the environment that you're in. That allows you to take, I'm getting new input that I didn't expect, what is a sensible thing to do here? And in a rat, we believe cortex was the beginning, the early mammals of building a model of the world. It was not a very good model, so it really was only really necessary when things were totally out of place. But it got better and better. So between rats and the last brain I'm going to draw, which will be in blue. This is the one you know. I'm not a good artist. It's a midbrain is kind of over here, hindbrain, spinal cord. Mostly, when you look at a picture of your brain, you only see forebrain. It's swallowed the rest of the entire system. This flat sheet that folded over has now folded up on top of itself. It is a system that got really, really, really good at building models of the world. So good that between rats and us, you have the rest of primates who use that model of the world now, not to just deal with unexpected things, but to control basic movements. They did this because, and I believe, primates evolved direct control of their movement with forebrain for the first time because it allowed them to move in environments that were much more dynamic, unpredictable, and constantly perturbing them, like the tree canopy. It's a shocking fact to me that the only large thing that can live in the tree canopy with unstable branches and move around elegantly is a primate, or things with wings or sticky feet. So this is the beginnings. So around here, monkey. They started to use the model of the world they have now to control movement, and something crazy happens, which maybe you can anticipate. This means when you watch a monkey move, if you remove part of their cortex, it's obvious. They're partially paralyzed. They don't do any of the behaviors they normally do, which was not true before this. But it also means if you're watching a monkey with cortex, their movements tell you about what their model is doing. It tells you about the model of the world. It tells you about what's going on in their cortex. If you put a bunch of primates together, they have a much easier time sharing what's going on in their mental model than you would for a mouse or a rat or any other species. That is the substrate necessary for building the kind of communication that we ultimately are best known for. Human language, what I'm trying to do now, is to put a model in my head, represented in my cortex, using direct control of my movements, although primarily now we use detailed articulations of our tongue and control of our windpipe. I'm trying to build a model in your head. And that is the fundamental basis that began with primates needing to figure out how to move elegantly through the trees that ultimately led to the superpowers of the human brain. Human intelligence.
3 minutes.
Good. We're about there. So what does this mean for text? Human language is the expression of one model and transmitting that through the control of movements to another cortex, another human brain. But that wasn't the end of the story. As it turned out, for you to really build a detailed mental model that's the same as mine, for me to effectively communicate with you, your model needs to be, I'm going to use another second thing I want you to remember, which I'll write in green, my use of text. Untether. You need to be able to model something that's not directly the result of your sensory experiences. So you need to be able to take your model and run it on data that is not coming in through your eyes, ears, and nose. That was not a very useful thing for a monkey in the trees to do. He should not, you would be selected against if this chimpanzee just imagined some fruit or a branch that behaved differently than the ones that actually were there. Them modeling the real world accurately was a good thing. But when it becomes now used for communicating, being able to untether your model, to think about aspects of the world that somebody is describing to you that are not directly in front of you, became finally a useful skill for the model to have. Maybe in the beginnings, these were humans who could untether, who were probably slightly psychotic, that had some weird neurotransmitter levels that made them capable of doing untethering, but largely now we call that abstraction. The ability to think about things that are not in fact really true. But that is necessary for human language to work. When the human brain untethered, this ability to communicate and coordinate our mental models was now basically what defines human society. When we decided that we needed to preserve basically the state of language. That's when you get to the creation of text. The abstract symbols that codify these thought processes. Now, it's not just, as it started out, maybe as a way of communicating language and preserving it in a physical medium, as I've learned even more today. It's not in any way tethered to just language. It can represent all sorts of abstract things. What I believe the future of a physical instantiation of abstract thought should look like, or if you want to say the future of text, is that we need to take into account some of the things that we have learned from the past 500 million years of brains. One, as we've already hinted, is that these tools should be things that you can play around with, you can explore, and I think a lot of you are working very, very hard on this. The last note I want to leave you with is to tell you one last story. Do I have a minute?
30 seconds.
This is the shortest time this story's ever been told, of what the very, very, very tip, the foremost part of forebrain is doing, and what I think this means for text and our models. This actually folds around under here, and it's a part of the brain called the hippocampus. And if you look at the tip of forebrain, what it represents in the model below is space. You record from cells in this area, and they tell you where you are in an environment. That's cool. It's a system that we all need to have. Humans have it. It's buried underneath the rest of these folds. But if you remove it in a human, which has happened during surgery, they are slightly bad at navigating space, but they are very bad at storing memories. A human without hippocampus will never store another memory. And this connection between where you are in space and how we organize and store information is fundamental to how the human brain works. What I believe the future of text has to be is not a 2D document, but find a way to put and manipulate abstract symbols in a spatial context, which has technologically been very, very, very hard to do until, as we now know, is probably as I think Engelbart wanted. That's doable, but I have never seen a 3D Word document that I can move around with and use my system to its fullest potential.
Thank you. So we've lost 5 minutes, so we're moving along into the next coffee break. So we still do have 5 minutes of questions. Yes?
I thought of architecture there at the end, right? Like we have space already, and so I could speak about how the uses of existing of space and design in space might merge with text.
Somehow I spend a lot of time talking with architects, and I think maybe for these very reasons. One thing that's already been brought up, the person who worked for the cabinet office mentioned the people fighting with Word would instead have a bunch of spray glue where they would go and put things in their environment. I'll tell you the type that I want every single light in this room to be actually a micro laser projector where every then surface could potentially support presenting information, and I want to compose what I'm working on or what story I'm telling in my environment. Now, you could put a VR or AR headset on and get space, but then you lose the other amazing thing that humans were so good at, which is coordinating amongst others. And this asocial aspect of the current versions of these things, I find a non-starter. It will hopefully improve. But just simply spatializing information would be step one, and I believe it's quite doable. And building our future built environments around that notion. So post-screen, everything becomes the top. Then you have to figure out how to organize an archive. Yes?
Are you sure you got the right model? Because as someone who's got 40 years Alexander technique behind them, Tai Chi and all that, most of the learning is not through spatial awareness, but through the body's response. And if the body feels good in doing something, it will continue doing something.
Yeah.
If it feels bad about doing something. So the model alternate model, which started being built in 2007, first international conference on fascia, Harvard Medical School, is the fascia, which is a connecting bit throughout the body. It has thousands of nerve endings which feed into the brain, and that modifies the thinking processes in the brain, which then decides to do something or not, or how much effort to put into something, which is very different from the spatial model.
I 100% agree. Well, no, I 33% agree. Because I'm going to use this opportunity, thank you very much for asking this. our future tech, as well as our model of how this works, need to include exactly what you said, but I didn't have time to in this talk. It needs to be spatial, social, which I implied when talking about VR, and exactly as you're saying, it has to be physical. It has to be embodied. These are all the three key components of the model that need to be, we rely on those for organizing, understanding our world and our information. And if you think about what modern forms of tech have done to information, every single one of these things has been deteriorated.
Yeah, it's all there.
Yeah.
Harold, really quickly,
Yeah,
please.
I've got a quick question, which isn't about your talk, but I'm sure the answer will be about your talk. You didn't really mention the body, and I've always wondered, people go around saying human, the brain mass, body mass, we're the best, and yet elephants and whales have got much bigger brains.
Yeah.
Why isn't it just the size of the brain that matters? What's the body got to do with that?
So the size of the brain, the biggest brain, it's probably a blue whale, right? The biggest cortex is in the dolphin, and it's also very striated. And what's very interesting about dolphins, I think they might actually have a better model of the world than us, but they have no connection between cortex and their movement system. So there's attractive neurons that go from motor cortex to muscles, which I'm using now to speak and move around. And this is lacked in dolphins, it's just branched off pre-primate. And so a lot of that intelligence they likely have living in a modern world is trapped inside multiple layers that I think the means in which they can coordinate their form of communication, I would argue, is fundamentally different than what we achieve by communicating directly with cortex to one another.
And of course, cephalopods have done it in a different way altogether.
Yes, and the other half of my language
Because
is
they have
cuttlefish.
more barriers.
10 minutes is short.